Hello everyone. In this video, I want to show you a nice, very powerful tool in Simulink for Robotics Toolbox, using which you can perform some robotics tasks much more conveniently and without writing extensive amount of code. So one of the projects that I give to my students in robotics classes is a basically path planning trajectory generation with the SCARA robot to write something. And for that, I give them basically some STL files of 4 links for a SCARA robot like these. Then I give them some data of the points in time that the end effector of the SCARA should be. So basically give them XYZ location of the end effector as well as the Z angle. And I can give them in something like this, right? So let me show you here. These are the data that I have. So the time goes from 0 to 24 seconds. On the left side, the first column is T, time. The data are not equally spaced. And then the next 4 columns are X, Y, Z of the end effector as in meters, as well as the angle Z of the end effector in radians. And then what do I ask them? I ask them to create a trajectory for this robot using cubic splines, so that the robot goes from one point to the next, and basically these points correspond to writing something. Okay. Now, since these points are not equally spaced in time, as you can see, it jumps from 0 to 0.5, then from 0.5 to 3, 4, and then you see they are not equally spaced. One of the first thing I ask them is to create a lot more data than what originally is given. And for that, I ask them to use cubic splines. So they're going to perform cubic spline interpolation and fill in between these data points with an increment of 0.1. So if I have nothing between 0 to 0.5 in the beginning, after the interpolation, they should have data at 0, at 0.1, 0.2, 0.3, 0.4, 0.5, and an increment of 0.1 all the way to 24. So now instead of 24 5 points, they're going to have 240 something data points, a lot more, and that makes their simulation and animation a lot smoother. Okay, because now you have a lot of more data points and all equally spaced in time. So the first thing is to increase the size of these task points in the joint space, in the workspace or task space, using a spline. And for that, they have to write a code, of course, to perform cubic spline. You see here is a sample code that one of my students wrote. And here you can clearly see the coefficient matrix, the right-hand side matrix, and then calculating the coefficient, and then running that function over and over in a for loop to increase with time, as I said, in time increment of 0.1 to make the number of points a lot more. Now that you have all these data points, it is time to for each one of them, because they are in the task space, now you have to perform inverse kinematics for the SCARA robot to convert them into Q space. So they have to write an inverse kinematics function for the SCARA robot and give it the geometry of the robot and the pose, and it gives you all of the basically the 3 angles as well as the prismatic value for the third joint. Now that you have these Q values, it's time to plot the robot for each one of these set of joint values. So they write another function that takes these joint values and it plots the SCARA. So it has the geometry, it reads those STL files that are provided to them. It sets a fixed view. First, it assembles the robot, because each one of those STL files are only centered at origin at identity rotation matrix. So now they have to move them and translate them up and down, properly assemble them, and then rotate and move the joints, and then use the patch command to plot the STL files. Okay, and this is the file STL read. This is not the default STL read of MATLAB. This is a different STL read that is available on MathWork website, MathWork File Exchange. So you see, in order to achieve this simple task, they have to write a main script, a cubic polynomial function, inverse kinematic function, plot robot function, which takes as a utility function the STL read. And let me show you what it does before I want to talk about the main topic. So here is the robot from this angle. Okay, and you clearly see its patch command. You see all of these triangles from the STL file, and it is writing something. Now, okay, now I did not put the line that it is writing. It's basically writing my family name. Yeah, you might say a little bit selfish, huh? No, actually, it was easy actually to have the students have the SCARA write a few letters. It's not my entire family name actually. So this is what they achieved in the project. Okay, now, instead of all of these code, there is another simpler way to do it, and this is using the building blocks in Robotics Toolbox for Simulink. So here, look, we're going to achieve all of that in only 3 blocks here. One that performs the cubic spline, one that performs inverse kinematics, and one that performs the simulation or the animation of the robot. So how do we do that? First, we need to run this simple code here. This first one called Robotics Toolbox Demo. What does this do? It only is a few lines of code. As you can see, 1, 2, 3, 4, 5 lines. That's all it is. First, of course, it reads that text file that has all of these data points in it for the path, the name, basically, that the robot is going to write. Separate the time values from the pose values, which is X, Y, Z, and psi. Okay. You need to have some velocity conditions at each waypoint, which here we're going to use a bunch of zeros. The same thing was used in those codes. So when it reaches to each one of the waypoints, it momentarily stops, then it moves on. And then what is the robot? The robot, you don't need to bring a bunch of STL files. All you need is to use this command, load the robot, and bring a SCARA robot and perform the job. Now, this SCARA robot that I'm bringing is different from the one that you can see in this guy. This is a Yamaha robot. This is an Omron eCobra 600, but it is a SCARA robot anyways. So now look, if you want to know a little bit more about it, look up this command, load robot. Look it up on Google or MathWork. And it says, hey, just give the name of the robot. It brings it as what we call a rigid body tree object. So it imports it into MATLAB, and you can use it. And actually, I don't really need to do that. I do not really need this. Here, I just use this command for more information, but really I'll show you in Simulink, you can even pick this and you don't even need to run this line of code. Okay, and instead of this part here, which you read this text file, you can bring in from file command. Okay, so you can export this data, this task. Now I can go ahead and export this task or this T and pose vector to different files, and I can bring them into Simulink. And instead of giving them here separately, you see here, this constant called pose vector and this other constant are T values, I can read them from a file. So I can use the from file block, right, as you know. And I can just directly read them from a math file, just like that. Okay, so I do not even need to run this script at all. And these velocity boundary conditions, I can easily just set it to a bunch of zeros. So I can just go with running the Simulink and not doing any script. So now, here, look, these are the XYZ inside the pose of the end effector. This is the time values, and you also need the clock for the time. This is the block that you have called cubic spline trajectory generator. Now, that's not the actual name of it. This is what I called it. The actual name is just called polynomial trajectory. And you can find it under basically MATLAB Toolbox. Let me show you here. So if we go to help, you can see that it is available under Robotic System Toolbox. Okay, so Robotic System Toolbox has a bunch of blocks, and I can also show you that from here. Let me actually show you from here. That might be more useful. There we go. You see here, Robotic System Toolbox, and there are different things that you can do, and there are some tools for 3D simulation. One of them is basically this block here, Simulation 3D Robot, and the other one is to set up the scene, this one. So these two are two of the blocks that I used. And then you can go and look at the other blocks that are available. So if we go here under utilities, let me see if I can show you some stuff here. Look, that is this guy, polynomial trajectory. You see? And when you click on this, you can either type those waypoints directly here, or instead of saying waypoint source internal, you can make it external. And now it allows you to bring the waypoints and the time points like I did from a separate block. Okay. And then the output of this are going to be Q's, Q dots and Q double dots. So Q's, omegas, and alphas, or V's and A's, velocities and accelerations. And the method could be cubic polynomial, quintic polynomial, or B-spline. Okay, here we want the cubic polynomial, so that's what we use. Now, what is the size for these waypoints? If you look, the waypoints, the dimension of it, that's very important, is n by p, where n is the number of data points per waypoint. Here is x, y, z, and psi, so 4. And p is the number of waypoints. So if I have 24 waypoints, and each one has 4 data or 4 values, then the matrix that you enter should be 4 by 24 in my case, right? Time points should be 24 by 1, a column vector and 1 time point per waypoint. Okay, and this time directly comes from the clock block here. So this is how you set this first one. So instead of doing those that code that I showed you that find the coefficient matrix, the right-hand side, and a for loop to perform and increase the number of data points, all you need to do is to use this block. Simple as that. Very, very simple and very fast. Okay? And if you look at this end effector, you see sample time infinity, time values infinity, but if you want, you can sample them every 0.1 of a second or something too, but this is good. So here it spits out Q, Q dot, and Q double dot. We don't care in this project about velocity and acceleration. All we care are the Qs. Now, instead of writing a separate code for inverse kinematics of this robot, we can use the inverse kinematics block. That's another powerful tool that you have, the inverse kinematics. This one, which is also available, I'll show you under the robotics toolbox. Here, you see, you can give it a rigid body tree name. So here you see it's called Amran a Cobra 600. This is the variable name coming from this load robot command. So when I loaded this SCARA robot, I called it this. So now I'm referring to that and say, hey, the variable in the workspace with this name, that is the robot you need to do inverse kinematics for. Okay, you see here, that variable is there. And you can pick the end effector to be any of the links. So here is link 4. I show you, you can change it. So this one is there. Then it performs the inverse kinematics in general numerically. It does perform it numerically, so it can apply it for a lot of different robots. And the way that it does it is either with a version of gradient descent algorithm, which is called BFGS, or with the Levenberg-Marquardt. If you do Levenberg-Marquardt, you can set up parameters. There are exit conditions for the while loop of the numeric solver, right? And so on and so forth, and enforces joint limits. So you cannot ask the robot to go beyond its mechanical or physical joint limits. Okay, so that just performs the inverse kinematics. You don't need to do anything. You just need to pass to it 3 inputs. What are these? The pose of the end effector, but not as 4 values x, y, z, and psi only. It should be a 4x4 homogeneous transformation matrix. So you have to get those x, y, z, and psi from the cubic spline trajectory generator and convert them into a 4x4 matrix. So here we are using a MATLAB function, and we are getting the q vector, which has x, y, z, and psi. As you can see, we separate the component, and then we form the 4x4 homogeneous transformation matrix, call it pose. So this is this is H matrix, and then that is going into the robot. It has weights, which are basically the weights for the joints. Let me show you. Okay, so here you can see it's 1/6 vector of weights on the tolerances for orientation and position of the end effector. So if some position components of the end effector are more important than the orientation components, the first 3 are x, y, z of the end effector, the next are the 3 Euler angles of the end effector. If, for instance, you care more about the end effector being in position than you care about the angle of it, then you can use tighter tolerances for the x, y, z, the first 3 values, and not care too much about the next 3 values. Okay, for a writing purpose, you might not care too much about the angle of the end effector. What you care about is x, y, z, because you're writing on a flat piece of paper. Now here I have given them all the same weight, but as I said, you can use tighter tolerances on these first 3 and lighter tolerances on these last 3. Okay, so this is the weight. And then you need initial guesses, because it's a numeric solver. You always have to have initial guesses. Now, the trick that is used here, and one of my students did very sharply, and I really liked it, is instead of giving it some basically 4 initial numbers for constant values, which are initial guesses for theta 1, theta 2, d3, and theta 4 of this SCARA robot, he used a delay unit, and the answer, which are the actual theta 1, 2, d3, and theta 4, he used them with 1 unit delay time and gave it back to the robot as initial guess, which is really cool. It also sends out some information about the solution of the inverse kinematics, which I terminated because I don't need them. The same thing I did for velocity and acceleration of these waypoints. Now that you have the configuration of the robot, which are the 4 joint values, you can pass them to the simulation block. And what you need to give to this guy is what is the robot that you are trying to simulate. And here you can either say it's a rigid body tree object and then give it the name, or say I'm gonna pick it from the library. And what is that? Here you have to select that. Okay, so you have to find that Omron robot here. Say, hey, this is this robot that you are. Give it a name, give it a sample time for simulation, and this will create the simulation. Now, in which environment? For that, you need this block here. And this guy is going to create the scene. Now, here you can see there are different types of scenes that you can either get from MATLAB, the ones that are available, or you can create some yourself, you see, like this, and then browse for a file. So if there are some scenes like this one, you have already made some FBX or other virtual reality environments, you can bring them in. Or here, I just use some default scene which are available, and there is only empty space and double lane change. Okay, I'll show you both of them. And then here you can say what kind of view do you want. Do you want to see it from origin? Do you want to have a specific angles and position for the camera? Here I put it at custom. Put my camera at this location and this pitch roll pitch yaw angle. Give it some sample time for the 3D animation. You can even add weather, right? So you can add cloud, sun, fog, and make it more realistic. And now I assume we are ready to see the results. So first we run this code. There we go. And you can see that this is my Omron robot. You see it has 4 bodies. Link 1, 2, 3, and 4. There is a base. No gravity is applied. Now here it doesn't matter because we are not using kinetics equations. And the data for it is a structure. And if you want to see any of these links, the data for it, you can say, hey, give it the name of the variable and go to the field bodies and give it like here, link 2. Give me the data for link 2. Look here. So now you can see some of the data for link 2, which is 1x1 rigid body joint. It has this mass. Again, mass doesn't matter here. A center of mass, inertia, parent, children, visuals, and you see it is coming from STL file. But let me show you, when you run the simulation in MATLAB 3D animation in Simulink, it does not show those patchy blocks. It shows a lot better simulation animation and quality. Look here. Okay, compiling should be done, and it is gonna start it in a second. Here we go. The first time it's a little bit slow. After that, it's not going to be that bad. Here we go. You see? So this is that Omron SCARA robot, and that is the end effector. Now, of course, we did not, if we need a pen or something, we have to create a STL file for it and add it. Okay, but clearly you can see that, and you can use your mouse, and you can, of course, move around. Right? You can see the environment. You can right click. Look. See, you can right click here. Let's see if I can do a right click and show you. And it allows you to see the coordinate system and a bunch of more things. Okay, so clearly this is a lot more realistic and a lot less effort for simulation of this robot as opposed to writing all of those code. Okay, let me run it one more time. This time it should be fast. This time I ran it on the empty scene background as opposed to that 2-lane road or something. Okay, but again, you can make this environment yourself and make it as complicated as you want and make it look a lot nicer. So you see how much effort is saved, I would say, using just 3 blocks here, or maybe 4. Because this block is not fundamental, is these 2. Of course, if you don't have that block, you cannot have a scene, so you have to have it, but setting that to very fancy environment, that's not really the goal of this project. The goal is to perform a path planning and inverse kinematics for a robot. So I showed you where to find these blocks here. You see, there are different types of polynomial rotation trajectory, transform trajectory. There is this guy here that converts any transformation to any other one, so it can get quaternion and convert it to rotation matrix or any other one, right? So it can convert Euler angles, for instance, to, I don't know, axis angle or anything else, or a rotation matrix, right? Or homogeneous transformation. So these blocks are very, very good. So utilities, 3D simulation. Now mobile robot algorithms. You see here, we have some kinematic models for unicycle, for differential drive robot, for bicycle, for Ackermann geometry, which is for cars basically. Then we have manipulator algorithms. Look, so you can do forward kinematics for any of these robots. Now, by the way, which robots? Let me show you. As I said, there is a big library of robots. And here, if you look under this load robot command, you can see them. So there are all sorts of ABB robots, and then there are mobile robots here. There is the Atlas from Boston Dynamics. Mobile robots, again, there is the Turtlebot, there is Fanuc, and lots, okay? You see several degrees of freedom. So manipulators, mobile robots, humanoid robots. You can see KUKA, and this is the one that we just used, the Omron. That's the only SCARA that there is, okay? And then there is Puma, Quanzer, and more. So you have a huge library of robots, and you can use each and every one of them. Now, so you can do forward kinematics for all of them, inverse kinematics for all of them, as you can see, inverse dynamics for them. You can get their Jacobians by just passing them the joints, right? And there are lots and lots of things you can see. So you don't need to do any of these calculations. They have already been calculated, and you can just use the block. There is motion model, there is task space, velocity product, torque, right? And then, of course, the gazebo, which is its own thing. We don't want to discuss that here. So I just wanted to show you the power of some of these blocks and how many robots you have, and you can perform many tasks much more conveniently. So hopefully this is useful to you, and I'll see you in the next video. Thank you.